There are rules to snake biology, not suggestions, rules. Constraints built into the lineage over 100 million years that define what a snake can be, how large it can grow, what it can eat, what thermal environment it requires to function, and what ecological role it occupies. The rules are consistent enough across living species that herpetologists can make reliable predictions about any snake from basic measurements. Body length implies mass. Mass implies prey size. Prey size implies habitat. Habitat implies thermal range. The variables connect. Titanoboa cerrejonensis broke all of them. Not in the way that exceptional individuals occasionally push the boundaries of what a species normally produces. Titanoboa didn't bend the rules at the margins. It operated in a different biological register entirely. At a scale, and in an ecological position, that the rules governing modern snake biology would predict to be impossible. Every model that works for living constrictors fails when applied to Titanoboa. A snake longer than a city bus, capable of killing crocodilians the size of modern cars. And between those two wrongnesses is one of the more precise windows into deep time that paleontology has produced from a single fossil site. The largest confirmed green anaconda on record measured 5.21 meters. The largest reliably documented reticulated python reached 6.95 meters. Those are the upper boundaries of living snake biology, the extreme edge of what modern constrictors produce. Titanoboa cerrejonensis was 13 meters long. Weight estimates reach 1,135 kilograms. Those numbers do not describe a larger anaconda. They describe a different category of animal that happens to share the same body plan. The scaling relationships that connect length to mass in modern constrictors produce a curve, and Titanoboa sits so far outside that curve that the graph stops being useful. So the question isn't how big it was. The measurements answer that. The question is why nothing alive today comes close, and whether the limits preventing modern snakes from reaching that size are biological, ecological, or thermal. The answer is all three. Snakes are ectotherms. Their metabolism, digestion, immune function, and muscular performance all depend directly on ambient temperature. That dependency places a practical ceiling on how large an ectotherm can grow in a given environment. Larger bodies exchange heat differently, and at some point the thermal demands of keeping that mass functional exceed what the environment can provide. Apply modern ectotherm-sized temperature models to Titanoboa's mass, and the output is a world significantly hotter than any modern tropical environment sustains consistently. Its size implies a climate the present can't produce. That is not a minor detail. Titanoboa's dimensions are not just a measurement. They are a constraint violation. The biological rules that cap modern snake size at under 7 meters did not apply in Paleocene Colombia, and Titanoboa is the proof. The vertebrae from the Cerrejon coal mine were so large that the paleontologists who first examined them recalibrated their estimates multiple times, not because the method was uncertain, because the numbers were so far outside expectation that error seemed easier to believe than the fossil. The fossils weren't wrong, the expectations were. 6 million years before Titanoboa existed, the Cretaceous ended. Not gradually. The Chicxulub impact triggered a collapse of global ecosystems so severe that 76% of all species disappeared, dismantling the food webs that had structured life for 165 million years. What remained was vacancy. Not emptiness, the Paleocene was biologically active, but a world where the largest ecological roles were suddenly open. The giant predators were gone. The giant herbivores were gone. The upper levels of the food chain had been erased. In what is now northern Colombia, the Cerrejon Formation sat near the equator during this rebuilding phase. Around 58 to 60 million years ago, the region was a dense tropical rainforest threaded with rivers and swamps. The coal seams mined there today are compressed Paleocene forests, preserving the animals that lived within them. But the ecosystem recorded in Cerrejón was not normal. Extreme equatorial heat, extraordinary biological productivity, and ecological vacancy combined to create conditions where multiple lineages grew unusually large at the same time. Giant turtles, giant crocodilians, and above them, a snake that modern biology says should not exist. The Paleocene tropics were hotter than today, and with the major predator lineages temporarily absent, the normal limits on body size were briefly lifted. Into that gap, a snake lineage expanded. It simply scaled existing ones into a size range no snake had reached before. The world that produced it wasn't operating under normal conditions, and that abnormal world is exactly what made Titanoboa possible. In 2009, a study published in Nature used Titanoboa's body mass to calculate something that had little to do with snakes. Herpetologists have long documented a relationship between maximum body size and environmental temperature in ectotherms. Given a temperature, you can estimate a size ceiling. Given a body size, you can estimate the temperature needed to sustain it. Applied to Titanoboa's estimated mass of 1,135 kilograms, the model produced a mean annual temperature for Paleocene Colombia of 30 to 34 degrees Celsius, centering around 32 to 33 degrees Celsius. That number was a problem. Prevailing paleoclimate models had estimated Paleocene tropical temperatures between 23 and 28 degrees Celsius. Titanoboa's calculation came in 4 to 9 degrees hotter than expected, a difference large enough to affect global climate models. The pushback was immediate. Critics argued the modern ectotherm model might not apply cleanly to extinct species, that the Cerrejón sample size was limited, or that the largest vertebrae might represent abnormal individuals rather than typical adults. But those objections had their own weaknesses. The temperature-body size relationship is based on fundamental ectotherm physiology, and explaining the fossils as pathological individuals would require multiple giant vertebrae from multiple animals to all represent abnormal growth. The debate remains unresolved. Later studies using other climate proxies have supported elevated Paleocene tropical temperatures, though the exact numbers are still contested. What Titanoboa ultimately did was force climate science to reconsider its assumptions. A snake that broke the rules of snake biology also disrupted the models used to understand ancient climate. The anomaly wasn't limited to the animal. It extended to the world that produced it. The skull of Titanoboa has not been recovered intact. That matters, because the skull is where feeding mechanics are understood most precisely. Jaw joints, tooth structure, gape angle, and the kinetic linkages that allow constrictors to swallow prey wider than their heads. Only partial cranial material from the Cerrejón Formation exists, enough to confirm the basic structure, but not the full mechanical picture. The Cerrejón Formation provides an important clue. The ecosystem included giant turtles such as Acherontomes and cerrejonemes with shells up to 1.7 meters wide, and crocodilians like Anthracosuchus reaching 4 to 5 meters in length. What fills the anatomical gap is comparative anatomy. Titanoboa belonged to the Boyne lineage, related to modern boas and anacondas, whose skull mechanics are well understood. Boyne snakes possess a kinetic skull with multiple movable joints. The quadrate bone rotates outward during feeding, widening the gape, while the two halves of the lower jaw are connected by elastic ligaments rather than fused bone, allowing them to spread apart. In modern anacondas, this system allows them to swallow prey much wider than their heads. Scaled to Titanoboa's 13-meter, 1,135 kilogram body, the question becomes what prey that feeding system could handle. These Cerrejón animals were not incidental neighbors. They were animals within the prey range of the ecosystem's apex predator. Bite-marked turtle shells from Cerrejón are consistent with large constrictor feeding. For comparison, The largest anacondas today occasionally take caimans 1.5 to 2 meters long. Titanoboa, operating with the same skull mechanics but at 3 times the mass, was likely processing prey in an entirely different size class. The feeding system itself was not new. It was the same Boyne mechanism, just operating in a size regime modern snakes never reach. The complete skull that would confirm every detail hasn't been found. But the fossils we do have show that the system worked, and that Titanoboa was consuming prey no living snake attempts today. Constriction is not squeezing. The common image of a snake slowly suffocating prey is incomplete. For much of the 20th century, scientists believed constrictors killed by causing respiratory arrest. Modern studies show something different: circulatory arrest. When a constrictor coils around prey, the pressure can exceed the animal's blood pressure, preventing the heart from refilling between beats. Blood stops reaching the brain, and the prey loses consciousness within seconds, not minutes. It doesn't run out of air. The blood simply stops moving. That mechanism changes how constriction scales with size. In snakes, constriction force depends on the muscle mass wrapped around the prey. As body mass increases, the force does not rise linearly. It follows a power law relationship, meaning larger snakes generate disproportionately greater pressure. At 1,135 kilograms, Titanoboa's constriction coils were operating in a completely different pressure range from modern constrictors. The prey it encountered, giant turtles and crocodilians like the 4-meter Anthracosuchus, had cardiovascular systems scaled to their own body size. Titanoboa's constriction force likely exceeded those thresholds almost instantly, collapsing circulation within moments. Studies of large modern pythons show prey losing consciousness in 6 to 14 seconds. At Titanoboa's scale, that timeline likely compressed even further. That matters for feeding. Prey that loses circulatory function immediately stops resisting, allowing the snake's kinetic skull to process large animals more efficiently. At Titanoboa's mass, constriction wasn't just stronger. The physics of the kill were fundamentally different. Snakes are not apex predators. Across their 100 million year history, they have mostly occupied the middle tiers of food webs, hunting smaller prey while remaining vulnerable to larger predators such as birds of prey, mammals, and large reptiles. Titanoboa was different. In the Cerrejon formation, it sat at the absolute top of the food chain, not simply a large snake, but the uncontested apex predator of its ecosystem. The reason lies in timing. The end Cretaceous extinction had removed the giant theropod predators that dominated ecosystems for 165 million years. In the early Paleocene, their ecological roles were temporarily vacant. The mammals and predatory birds that would later become top predators had not yet reached that scale. Into that gap, a snake lineage expanded. The Boyne body plan, constriction, and kinetic skull already existed. What changed was the environment: extreme tropical heat, extraordinary productivity, and an open apex niche. At 13 meters and over a ton in mass, Titanoboa simply scaled those existing tools into a size range no snake had reached before. Nothing in the Cerrejon ecosystem could hunt an adult Titanoboa. The giant turtles were harmless. The large crocodilians were prey. For a few million years in the early Paleocene, a snake ran the ecosystem. It happened because the normal limits of snake ecology briefly stopped applying. The green anaconda is the closest living reference for Titanoboa, not because the comparison works, but because it shows how far outside modern snake biology Titanoboa actually was. Eunectes murinus, the green anaconda, reaches about 5 to 6 meters and roughly 100 kilograms in the largest females. It is semi-aquatic, tropical, and lives in the Amazon and Orinoco basins. an environment similar to the swampy rivers of the Cerrejon Formation. But even as the closest ecological comparison, it is less than half Titanoboa's length and less than a tenth of its mass. The reticulated python holds the modern length record at 6.95 meters, but it is more slender and adapted for terrestrial ambush. Its largest prey includes deer, pigs, and occasionally small bears, already the extreme limit of what modern constrictors attempt. Titanoboa was 13 meters long and about 1,135 kilograms. Because body mass scales with the cube of length, that difference is not incremental. It is categorical. The prey ranges reflect the same gap. Modern anacondas rarely exceed prey around 60 to 80 kilograms. Titanoboa was likely taking animals in the hundreds of kilograms, including giant turtles and crocodilians. Behaviorally, the comparison also breaks down. Anacondas rely on water to support their weight and move efficiently, and Titanoboa likely did the same in Cerrejon's river systems. But an animal 10 times the mass of an anaconda was not simply doing the same thing at a larger scale. The comparison fails, and that failure is the point. Titanoboa has no true living analogue. Titanoboa didn't lose to another predator. It wasn't outcompeted or hunted into extinction. The rule that allowed it to exist, the link between ectotherm body size and temperature, is the same rule that ended it. After the Paleocene, the climate began to change. Following a brief warming spike known as the Paleocene-Eocene thermal maximum, the long cooling trend of the Cenozoic began. Global temperatures gradually declined, including in the tropics. The 32 to 33 degrees Celsius equatorial temperatures that Titanoboa's size implied did not persist. As the climate cooled toward modern tropical levels, the thermal ceiling that had allowed a 1,135 kilogram snake to function began to drop. That relationship works both ways. Hotter environments allow larger ectotherms. Cooler environments lower the maximum viable size. Titanoboa didn't disappear in a sudden extinction event. It disappeared as the size limit for snakes slowly shrank with the cooling climate. The lineage survived. Modern boas still exist, but the extreme body size the Paleocene briefly allowed faded back into the range modern temperatures support. In the end, Titanoboa vanished for the same reason it appeared. The world cooled, and the largest snake that ever lived no longer had a climate that could sustain it.